All right. So these are the things that we'll be looking at for chemistry. Um, let's just go straight into it. All right. So we know, remember electronic structure of an atom, right? Where you have the nucleus having the neutrons and the protons. Okay, don't forget the nucleus is where you have the neutrons and the protons. Okay, and that sum of the number of protons and number of neutrons would form your atomic mass. Okay, and while only the number of um, protons would be your atomic number. Okay, at mass number, sum of protons and neutrons, while atomic number is just the number of protons. Okay, so the other thing you need to remember is that the electrons are arranged around the neutrons in what? In shells. The first shell is the highest it can hold is 2 electrons. The second shell, the highest it can hold is 8 electrons. And the third shell, the highest 2 it can hold is 8. Okay, so and though it increases as it goes on, but just remember that fact. Okay, so there's a subtle question there that says, how does group number relate to atomic structure? If you remember that time that we discussed um, um, different atoms, we started with metals, the ones that are willing to do what? Give off the electron in their outermost shell. Why? Because the attractive forces between the protons in the nucleus at the center of the atom and the electrons at the outermost shell, the attraction is weak. Okay, so because of the way the atoms are shaped, it looks like they are bogus, right? So remember that um, the longer the distance or the bigger the atom, it will suggest that there is more distance between the center where the protons are and the outermost shell where um, the electrons, the ones that you call the valence electrons, the ones that are the extreme end, okay, are. Okay, so that's why metals, their atoms are usually quick to do what? Give off that last shell electrons. Okay, so let's remember that. So that's basically what influences where you group what. So you can imagine, look at this picture here that we have is a screenshot or a snapshot of your periodic table. Can you see that lithium and sodium are in the first group, okay, and they are metals. Okay, so if you look at them very well, let's look at lithium, for instance. Its atomic number is 3, while its mass number is 7. That means it has 4 neutrons, okay? So its atomic number is 3, meaning that it has 3 protons. If you want to do the breakdown of its electronic structure, you will see that when you break down 3, 3 is 2 plus 1. So that means 1 electron is in its outermost shell. Okay, so you can see there are only 2 shells for lithium. 1 electron is in its outermost shell, and that 1 electron is what determines which group it's in. Okay, same thing with sodium. Sodium is atomic number is 11. All right, so guess what? Its own electronic structure will be 281. How do I know? 2 plus 8 plus 1 will give me 11. Okay, so just factor that at the back of your mind. Be quick to tell how the electronic structure will look. So that's why you can see 3 shells for sodium at the, where you have Na there. All right. So of course, the first shell will contain 2, the next one will contain 8, and the last one will contain 1. And that one in the outermost shell is what will tell you that sodium is in group 1, okay, in the periodic table. The same thing applies to the other ones. Because of time, I may not be able to go through each of them, but I just went through the ones for group 1 so that you can understand what's going on there. Okay, so just in case you see any question that suggests to you, how does group number relate to electronic structure? You have an idea how that happens, okay? I hope possibly we'll see, the next thing we'll see will show us how what do you call it? The actual structure in terms of the size of the atom, would influence even the chemical properties. Something like a metal. Okay, why would it behave like a metal? Why would it do all the things that it does? For instance, why would the metal be able to conduct electricity? Okay, why would the metal have a structure whereby it's solid? Okay, and at room temperature, and then when it's heated sufficiently enough, it will do what? Melt.
Oh.
Or become molten, more like, so that it can be in a semi-fluid state. So we should also discuss that probably later. Okay, so this is just a breakdown of how the research of what gave rise to what we know today as atomic structure or the atomic model. Okay, but yeah, we'll just move on. This is just for information. Okay, but then maybe if there's anything I'm going to say, we just need to remember that electrons are orbiting. That means they are in shells, while the nucleus has a what? A positive charge on it as a result of what? The protons. Please remember, neutrons don't have any charge. That's the main reason why they are called neutrons. They are neutral. Okay. All right. And then electrons have negative charge. Okay. Let me see, any other thing? Okay, let's move on. Okay, so yeah, let's look at the things that we talked about: ionic bonding or ionic bonds, which I told you another name for ionic bonds is electrovalent bonds. Okay, so this happens between a metal and usually a non-metal, or something that behaves like a non-metal. At that point, the metal is the one that wants to totally give off, it's willing to yield its last electron. Why? Remember what I said, weak attractive forces between the neutron and the outermost shell. So it is, that's one that is in the outermost shell, is like it's being loosely held by the attractive forces between it and the nucleus. Okay, so if you have a question, just let me know. Let me see, at a point I may ask you for any input. All right. So, of course, the non-metal is the one that will do what? Be willing to receive an electron. And then I told you, there was something I told you, just as a recap of that. I'm not sure if it was the first class or the second class we had when you were still in Nigeria, that the reason why ionic bonds are so strong is because one is willing to totally give off its electron, while the other one has such a strong attraction for that electron that the other one is trying to give off, that it will want to pull it into itself. And the reason is that, it has somehow been explained that there's something called a stable state. And that stable state of now it's no longer going to be an atom, now it's going to be an ion. The stable state of an ion usually likes to have 8 electrons in its outermost shell. So because of that, for instance, think of sodium. Let's look at sodium chloride. Sodium chloride is, sodium is 281. So it is willing to give up that one that is at the extreme end so that it can just have 8 in what will now become its new outermost shell, okay, after it has become an ion. Remember, an atom that has lost an electron or gained an electron is no longer an atom, it's now an ion. Okay, of course, that makes sense why the name of the bond is called ionic bond. It's like I'm talking to myself. Explanation. Okay, so I was just trying to explain that, you know, an atom, right, that either loses an electron or gains an electron, you know, depending on whether it's a metal or a non-metal, right, is no longer an atom, but it's called an ion. Okay, it's called an ion. So for instance, sodium is 281. It will most likely want to release the last electron in its outermost shell so that it can become 28. Okay, now it will now become a positively charged ion. Why? Because it has more protons than electrons. Okay, remember, sodium is atomic number 11. So by having more protons in its nucleus than electrons, which is now 10, 2 plus 8, 10, you now have a positively charged sodium ion, which is represented as Na+. Then look at chlorine. Chlorine is 1735. That means its atomic number is 17. So imagine its shell will have 287. Okay, so you know that means chlorine 2 likes its outermost shell to be what? 8. So it will gladly try to receive that electron from sodium so that it will become 8 instead of 7. And because of that, it will have 18, it will seem to have 18 electrons in its outermost shell, and then have only 17 protons in the nucleus, which will now make it negatively charged. Why? Because of the number of electrons is more than the number of protons. Okay, so that's why you see that Cl has a minus on it because of that extra electron that it has. Okay, so that's the reason why the bonds, ionic bonds, are so strong, because one is strongly desiring to give off and the other one is strongly desiring to receive. Okay, so the bonds are usually strong. All right, so I think I've already answered those other questions. If an atom loses an electron, it has a positive charge. If an atom gains an electron, it has a negative charge. Okay, no longer, of course, it's no longer an atom anyway. Okay, so just confirm, do you understand what I just explained back then?
Yes, yes, yes.
Okay, cool. Okay, so the next type of bond we want to look at, okay, sorry, let me get through with the the ionic bonding. Then so there's this reference to giant ionic structures, uh, um, uh, but I think it's sort to, but you can think of it this way, that um, for instance, you have sodium chloride. Let's still use sodium chloride. Do you remember that sodium chloride, when you dissolve water, you dissolve salt in water, right? Sometimes those salt water can be a very good conductor of electricity. And that is so because of, you know, the fact that you have positive and negative ions in that solution. So um, without dissolving it in water, you can see that they have very high melting points because they have strong ionic bonds. Remember, I told you, I think I gave you an instance where if you try to melt common salt, okay, it will be a very high temperature and it will still not look like it's melting, okay, because of the ionic bonds. And then they can conduct electricity when they are dissolved in water, okay, when they're dissolved in water, or well, the other thing that you may find them dissolved in could be a solvent that's suitable for them. Okay, so maybe not all of them are totally soluble in water. Okay, so I think we can move on to covalent bonds. Okay, so covalent bonds happen between a non-metal and, of course, you can equally look at it too as a non-metal, usually between two non-metals. Okay, an example is H2O. Okay, that's covalent. Okay, that's water, right? H2O. So electrons are what? Shared. So it's in the difference between covalent and ionic is that instead of one to give off totally and the other one to receive totally, in that sense, covalent is that both of them are sharing it. Okay, so both of them are sharing it. They don't, it's not a total give off and it's not a total reception. Okay, so that's, you can just fill it in there that electrons are shared. Most small covalent compounds like oxygen and water are gases and liquids at room temperature. Okay, the reason for this is because the forces between the molecules are weak, but the covalent bonds are strong. Okay, so they're not totally, out of there, but they're not solid anyway. Okay, and the larger the mass of the covalent molecules, the higher either the melting point, sorry, the boiling point, or, okay, yeah, let's just say boiling point. Okay. All right. So that's for covalent. Just remember that the difference between covalent, the main thing you need to remember is the difference between ionic bonds and covalent bonds is that they are one is a total donor, if you like. One is giving and the other one is receiving in ion thing. Okay, like you have giant ionic structures, you also have giant covalent structures. Of course, you can guess that something like hydrocarbon, a hydrocarbon, which is usually made up of hydrogen and carbon, just, off the top of your head, you can guess that hydrogen and carbon. An example is diamond. Okay, diamond is, you can see it's hard and has high melting point and boiling point. Okay, as a result of the strong, in this case, yes, the covalent bonds are strong, and there's a crystal lattice that is formed. Okay, now we must observe that diamond cannot conduct electricity because it doesn't have any free electrons. There are no free electrons. All right, no free electrons are there in it. Graphite and diamond are both made of course, carbon. Okay, so carbon is what they are, that's common to them. And then the difference one may say is graphite. Graphite, you can liken graphite to what's used, the stuff that's used for pencil leads. Okay, which means technically it's soft, right? Whereas diamond is hard. um, and so those are the things that govern its property. The isotopes, I think one has an isotope. Graphite has an isotope, and diamond too is a different isotope of carbon. Okay, so the reason why graphite is soft is it doesn't have that crystal structure. Okay, if you look at the diagram there, there's a particular structure that diamond has. Diamond has the one on the left hand side, while graphite has the one on the right. It doesn't have a rigid crystal structure that like diamond. Okay, and of course, because of this, you can find graphite conducting electricity because it has some free electrons that can move around. Electricity is usually conducted by electrons that can move around and carry those charges from one point of the material to the other. Okay, so the last bond we want to look at in this discussion is the metallic bond. Okay, the metallic bond. All right. So of course you can guess metallic bonds, metals is between a metal and itself. The atoms of a metal. It's not between a metal and a non-metal. Covalent is usually between non-metal and a non-metal. Ionic is between a metal and a non-metal, whereas metallic is between the atoms of a metal. So think of iron, for instance. Iron is a solid at room temperature. Okay, so metals are generally like to give off electrons. They usually like to give off electrons to form positive ions. If you want to think of what's there in those spaces, they like to donate or give off electrons to form positive ions or lose electrons. Any word, okay, I think the technical term there is lose or free electrons. And I told you the reason for this is simply what? There's this state of stability every element wants to be in, where it has 8 electrons in its outermost shell. But because it may have 1 or 2 for the metals, I'm talking about metals now, it may have 1 or 2, it will rather like to give off that 1 or 2 in its outermost shell and leave the 8 in the one that is next to the outermost shell. Okay, so that's just that desire for stability that all elements exhibit. You can see, I can use that explanation and explain away most of the things I want to explain here. Okay, and you would have a very tight argument for anything you want. All right, so we move on. So these electrons being lost are all donated into the what? The pool. Is a pool. All right, so think about it in that sense. Pool of electrons. Okay, so these are free electrons, and because of that, now please take note. No, if you have a bond between a metal and another metal, think about it this way. They are not okay, they are not accepting electrons for themselves. It's just a pool. Okay, it's just a pool. Think of it like a collection of electrons. Okay, so properties of metals, they conduct electricity. Why? Because of those free electrons that they readily release. Okay, so of course they also have a tight crystal structure, except for metals like mercury, which is a liquid at room temperature. Okay, so of course there are some exceptions to the rule, but generally metals are rigid and they have a strong crystal structure between the atoms. All right, so do you have any questions so far?
No.
Okay. Okay. All right. So, okay, so if I'm going to, I'll just, maybe we should just talk about them in terms of um, their names. Okay, so if you look at, I think just as a point of reminder, carbon dioxide looks like this SO2. The only difference is that it's carbon that's in front of the O2. Okay, so that's carbon dioxide. While carbon monoxide is CO. Okay, so don't forget that. Mono means one, di means two. Okay, so sulfur dioxide, calcium carbonate. Of course, this one has another chemical name, but let's not bother with that for now. Calcium carbonate looks like this. And I told you that back then that carbonate, the NEAT, the ATE, okay, suggests that oxygen is there. All right, carbon is there too. Carbon 8, okay? So, sodium hydroxide, you can see how it looks, NaOH, hydroxide. Sulfuric acid is H2SO4. Hydrochloric acid is HCl. Copper sulfate, again, 8 in it suggests that there's oxygen in it. And sulfur shows up as sulf in the name, okay? Magnesium chloride, MgCl2, is what you have there for its representation. And then finally, sodium carbonate is Na2CO3. All right. So so there are a couple of formulas that we need to remember. The number of moles is given by mass divided by relative formula mass. Okay, so you know what? We'll come to these formulas if I'm not sure we've seen more questions that have this that require use of this. The ones that we've seen, I'm not sure if we've done paper 2, but in paper 2 we may see them. But number of moles is usually equal to mass over atomic mass, or in this case, relative formula mass, as the case may be. Okay, then in terms of volume, 1 cubic decimeter is equal to 1,000 cubic centimeters. And concentration of usually an acid or a base is, in terms of grams per dm³, is given by mass over the volume. So these are the clues that you need to remember. Make sure you always convert cubic centimeters to the cubic decimeters. Okay. Some other equations for you to remember, but we'll come to these much later. Okay. So do any of these look familiar? Okay, so some information, we don't have some information here. We would have done this, but yeah, we don't have some information here, like the relative atomic mass of sodium, magnesium, and calcium. So maybe we'll just move on. Okay, this next one suggests an experiment. Suggests an experiment. I'm not too sure which experiment it is, but it looks like this one is not too detailed. Okay, so are you familiar with electrolysis?
A little bit, yes.
Are you?
I'm a little.
Okay. Okay. All right. So the important thing to just remember is that if you can remember that um, like charges repel and unlike charges attract, it would help you a lot. Okay. So in an electrolytic solution, you just like I told you for sodium chloride, the sodium chloride will allow electricity flow through it. Why? Because of the ions inside it. Okay. So remember, inside a solution of salt, you don't have sodium atoms and chlorine atoms. No, you have sodium ions and chlorine ions. Okay. So that's why you can see here, the sodium ions, the positively charged ones, will go towards the negative electrode, while the negatively charged ones will go towards the positive electrode. And that's a summary of what happens during electrolysis in what is called an electrolyte. Okay, so this is usually the diagram showing how electrolysis happens. Okay, the the positive electrode is called the anode, while the negative electrode is called the cathode. That's just for us to. Sorry, let me free this guy up. I think. Okay. All right. Okay. Okay. So we can see the things that are behind there. So although we've said it, but just in case we want to be sure, the positive ion go to the negative electrode called the cathode, and are reduced, that's the gain electrons, while the negative ions go to the positive electrode and are oxidized in a process because they lose electrons. Ions are discharged at the electrodes, producing elements, and this is called electrolysis. Okay. All right. So let me see if okay, so let me say something about this. Now, remember that I said sodium is positively charged ion, right?
Yes.
So it would naturally go towards the negative electrode. Now, why is that? So that it can, remember, it wants to be stable again, right? So it will go towards the negatively charged, the negative electrode, because it will receive an electron, and that electron, of course, because of the attraction, but then because electrons with the potential difference will cause electrons to flow into the solution, and what do you call it? The sodium ions will now receive those electrons and become sodium atoms, right? Remember, they were missing one electron. So when they receive an electron, they will become atoms. For chlorine, the negatively charged ones, they will go towards the positive electrode. They are attracted towards it. And then they will give off the electrons, that the extra electron that they have, Cl minus. And when they give it off, it is those individual electrons that will now flow through the positive electrode and flow through the wire that connects the positive electrode to the negative electrode, and then you now have a complete circuit. Okay, that's why it's very correct to say that a solution like sodium chloride, which is made up of positive sodium atoms and negative chlorine ions, would form would perfectly conduct electricity. Now, it doesn't only happen for sodium chloride. It also happens for something like copper sulfate, where you have copper, Cu2 plus, positive ions, and you have sulfate ions, SO2, SO4, 2 minus, okay? So that is the same principle that happens. And at the end of the day, guess what will happen? By the time as electrolysis proceeds, guess what will happen? You will start noticing the negative electrode. Sodium will start forming on it, showing you that it's the sodium atoms are becoming more, okay, inside the solution. And guess what will happen? The solution will be becoming less salty because the things that made it salty are leaving it. Okay, so sodium atoms will start forming, and guess what will happen to the chlorine, guys? As the chlorine is losing its electron, it's becoming chlorine atom. And when two chlorine atoms come together, they form chlorine molecules. They become a gas. Okay, so there should be in this experiment, if you want to look at it as an electrolysis experiment, chlorine gas will be given off. Chlorine does not exist as individual atoms. They bond together and form chlorine gas. Okay, so that's just for what happens. And at a point, the solution will become totally free of both sodium ion and chlorine ion because electrolysis would have fully happened. Okay, so if you want to think of it, electrolysis is usually a way of collecting metals from solutions of those metals, and also a way of collecting gases in their purest form. So for instance, chlorine gas can be collected in its purest form. All right. So let's see. Let me see, is there anything I left here? Yeah, reduced. That's a gain of electrons, while a loss of electrons is oxidation. Okay, so there's a way I usually remember oxidation and versus reduction. Oxidation is usually addition of oxygen, of course, from the name oxidation. Oxidation is addition of oxygen, removal of hydrogen, and loss of electrons. Let me say it again. Addition of oxygen, removal of hydrogen, loss of electrons. While reduction, which is the opposite of oxidation, is removal of oxygen, addition of hydrogen, and gain of electrons. Okay, so you can think of it this way. When you want to define it, always start with oxygen. What happens to oxygen in each one? So how I remember it is, start with oxidation. Oxidation suggests oxygen is added, right? Then addition of oxygen, the other two, hydrogen and electrons, is a loss on their part. Removal, loss. Oxygen, addition of electrons. Then flip it on the side of reduction. Reduction is the opposite of oxidation. So addition of oxygen for reduction will become removal of oxygen. Removal of hydrogen for oxidation will become addition of hydrogen for reduction. And then finally, loss of electrons for oxidation will become gain of electrons for reduction. Okay. So, did you get that?
Yes.
Okay. All right. This next one is just basically an exercise, but like I said, I think if you took note of everything I said, um, it will be easy to sort out. So just because of time, let's move on. But okay, maybe I should just give the answers to this one. So for gain of electrons, we've already seen what this one is. This is reduction. Gain of electrons, that's reduction. Okay, reduction. So that's reduction we fill in this place for 2. Ionic compound. An ionic compound, molten or aqueous, that's carrying current is the electrolyte. Okay, that's what it means, electrolyte. The next one, the charge on the ions that go to the cathode. Remember, the cathode is the negatively charged electrode. The negatively
Yes.
charged electrode. And that's the one that will attract the positive what? Ions. So the charge on the ions that go to the electrode are positive. Okay. The name of the positive electrode is the anode. Okay. Of course, while cathode is the name of the negatively charged negative electrode. Sorry. The charge on ions that go to the anode, because the anode is positive, the charge on the ions will be what? Negative. Remember, unlike charges attract, okay, while like charges repel. So these ones are what? They are positive. Then what next? Let's say positive. They are negative, sorry. So the positive electrode will attract the negative ions. Okay. The charge on the ions that go to the anode will be negative, while what is made at the anode, if there are halide ions present, halide is suggestive of halogens. Halogens are where you have chlorine, fluorine, and the likes. That's the name of their group, halogens. Okay, so if negative ions will go to the anode, then what will be formed at the anode when they give up their electrons will be what? Whatever it is that they are. So in this case, if it is chlorine, when chlorine gives off its electrons, it will form chlorine gas. Okay. So in other words, it's halogen, the gas of that particular halogen that will be formed. And then the name of the negative electrode, of course, somehow they've given us the name. That's the cathode. And the loss of electrons is the opposite of gain of electrons. So that means loss of electrons will be oxidation. Okay. All right. So I'll just move on now. Okay. 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 So so I'm just going to state what should be in these ones. The answers are already at the bottom there, so we'll just fill them in. In a there's one word that is missing here, but let me see if we can fill it up. So there are two possibilities that I see here. In a system or in a reaction, energy is always conserved. It's always conserved. Okay, that's the law of conservation of energy. All right, it is never lost or gained. Okay, that's the law of conservation of energy. Okay.
Yeah.
In a system, yeah, in a reactive system. Then some reactions, I think that's the word, yes. So we can say it's reactions. So in a reaction, energy is always conserved. It is never lost or gained. Okay, so let's move on. It says some reactions give out energy, making the surroundings hot or warmer. Okay, if something gives out heat, imagine we're talking about energy now in terms of heat energy. Okay, so if a reaction gives out heat energy, just imagine what will happen. It will make the surroundings to be warmer. Okay, so that's the word there, warmer. These are called, remember, out. Anytime you hear the word out, always remember, I try to connect it with your knowledge of biology, right? I've forgotten the class of animals that, is it anthropes or so, where cockroaches, beetles, spiders, all of them that have their skeletons outside for protection, okay? They are called, those skeletons are called exoskeletons. So you see that word exo, it has qualified the skeleton somehow. Exoskeleton, outside. So the same thing here. Exo, if you understand that exo means out, then that means reactions that give out energy are usually called exothermic.
Yeah.
These are called exothermic. So that's the word exo there, looking at you there, waiting for you to select it. So exo should be there, okay? Then the next thing that we want to move on is the opposite of exothermic reaction, which obviously reactions taking energy, heat energy again, from their surroundings. If you suck out heat from the surroundings, it will make surroundings cooler. That's the principle on which your air conditioner works. That's the principle on which your freezer works. It simply sucks out what? Heat from the inside of the freezer, or from the room that the AC was installed in, sucking out heat. And when it sucks out that heat, of course, something else we have to suffer for that. So if you I don't know whether you've noticed it before, usually the outsides of your freezer are usually hot or warm. Okay, the outsides of your freezer are usually hot or warm. Okay, that's to show you that it has sucked out the heat from the interior of the freezer. Okay, so when some reactions take in energy, they absorb energy from the surroundings. It makes the surroundings to be what? Cooler or colder. Okay, and these are called endothermic reactions. Okay, they are called endothermic reactions. Do you have any questions with what I've said so far?
No.
Okay, but can you relate to it? Is this something that you can remember we've discussed before?
Yes.
Okay, all right. So we move on. Okay, it says, okay, this is just like an exercise. It says draw a reaction profile and define the type of reaction. Okay, so let me see. Okay, let me see if can I draw with this guy. Would this allow me to draw? I've always been, let me see if I can I add to this? Okay. Ah, okay, let me try this. Oh, that's nice. I can do that. Okay. Okay, nice, cool. Okay. Okay, let me do this. All right, so I wanted to see if I can draw a curve using some of the shapes here. So I found that I can actually do it. So if you remember, for exothermic, right? Exothermic reactions give off energy to the surroundings, making it warmer. So what that means is that the energy, remember, reactants will form products. Reactants will form products. Don't forget what I just said. Reactants will react together to form products. Okay. So for exothermic reaction, what it means is that it will give off heat, which means that that heat was originally inside the reactants at the beginning of the reaction. Just just follow my process of thought, okay? The heat was originally inside the reactants, but when they now combine together to form the heat of the product will now reduce. Why? Because that heat that was in the reactants was given off into the what? The surroundings. So in other words, the heat of the reactants will be more than the heat of the product because the heat has been given out to the surroundings, leaving the heat of the products to be lower than that of the reactants. Now, the difference, because that why I'm saying this is it will govern what I'm going to draw here. It means that let's imagine it in our mind. H of products, heat of products minus heat of reactants will be a negative number. Okay? Just like in mathematics, when you have something like 2 minus 6, a small number minus a big number, you will always have minus something, isn't it?
Yes.
Okay. So the energy of a reaction is given by heat of products minus heat of reactants. So if in an exothermic reaction, heat energy is given out to the surroundings, it means that that energy was stored up, locked up inside the reactants. And so that means that the heat of the reactants was more than the heat of the product, because that products with smaller heat than the reactant. So heat of product, remember HP minus HR for an exothermic reaction will be negative. Okay, so if so that tells me that this first graph on my left hand side, where you have energy against progress of the reaction, the heat of the reactants is higher, and that makes sense. It's higher. So if I'm going to draw its graph, let me see if I can quickly do that. It's going to look something like this. Okay.
So it starts high and then keeps rising.
Yes, it's going to
And then, okay.
Okay, can you see what I'm doing?
Yes.
Okay, so it's going to drop. The heat of the products will be lower than it. So that's how it's going to look. Sorry, let me change the color so you can see it. So that's how it's going to look.
Okay.
The heat of the products, right, will be lower.
Because it's released all of the
yes. The heat of the product. So if we were to put something like this here, let me see if I can quickly do that. This would be products. Okay.
Okay.
Yes. Something like that. Okay. Then, of course, the opposite is the case for this one. So because of time, let me just flip this around. but I'm going to flip it. Okay. Align, rotate. Okay, that's it. Flip horizontal. Yes, that's it. Okay. So that's how it's going to look. And then, of course, my products in this case is going to be all the way up there. Okay. And we can explain it. Now, if you wanted to explain for endothermic, it's simple. Remember, endothermic absorbs heat from the surroundings. So now I want you to imagine this. It means that the reactant started with a heat level lower than what they ended up with. Okay, so in the case of exothermic, reactants have higher heat, and that's what they eventually released into the surroundings. But in the case of endothermic, the reactants have lower heat than that of the product. That is why they absorbed it from the surroundings. So all that heat that was absorbed from the surroundings ended up with the product, because that's where the reaction will end. The products now have higher heat than the reactants. So when you want to now calculate the energy for an endothermic reaction, guess what? It's going to be positive. Why? Because by the time you say heat of products, which is higher, minus heat of reactants, which is lower, what will you have? You will have a positive number all the time. So if you want to label these graphs safely, you can do this. Let me just put the label beside each one. So this is exothermic, exo, and while this one is what? Endo. Yeah. Okay. So did you get that explanation?
Yes.
Okay. All right. Okay. Please don't forget that thing I said. Exo is out and endo is in. Okay. So these are the answers for the ones that had questions. Of course, okay, yes, of course. I think we've alluded to this, that the group number is the same as the number of the outer shell electron. Yes, look at it there. Lithium and sodium both have one electron in their outermost shell, which they are very willing to give off. Okay, but that's the reason why they're in group 1. Same thing with, I think that's beryllium and magnesium, okay? They have 2 electrons in their outermost shell. How do we know? Look at the atomic number, it's 4. So that means and remember, atomic number is the number of protons, but it's logical that the number of electrons is also equal to the number of what? Protons for an atom. So that's why you can simply look at 4 and break it down. 2 plus 2 is 4. Same thing with magnesium, the one under beryllium, which is 12. So 2 plus 8, 10, plus 2, 12. The outermost 2, the one on the right-hand side, extreme right, is what tells us that beryllium and magnesium should both be in group 2. Okay, let's look at group 3. Boron and aluminium. Okay, 2 plus 3 is 5, obviously, and the 3 in the outermost shell tells us that these guys should be in group 3. Okay, same thing with carbon and silicon. Okay, those guys are in group 4. Why? Because the number of electrons in their outermost shell is what? 4. Of course, you should know by now that we have moved from, we are gradually moving from metal to non-metal. Now, if you look at it very well, carbon is typically a non-metal. It's a non-metal. However, some of the compounds that it plays a role in, it seems to want to have that, semi-metallic property. Semi, like I said, semi, it's not a metal. So it just wants to behave like one, okay? But it's not a metal, but it wants to behave like one. But anyways, that's the whole idea. It seems it likes to gain electrons so that it will have its own, what do you call it? Or so it tries to lose electrons, not gain, sorry, please. It tries to lose electrons, just the same way sodium and magnesium, the metals, will behave, so that its outermost shell will be left with two, okay, two electrons. So I forgot to say something. Stability for atoms or for ions is usually either it has two electrons in its new outermost shell, or 8 electrons in its new outermost shell. Okay, so that's how it usually behaves. Of course, you can see silicon there representing with 14, and that's 284. It will likely want to give off that 4 to have 8 in its new outermost shell as an ion. And then finally, nitrogen and phosphorus, both of them have 5 in their outermost shell, and that's why they're in group 5. Okay, so this is the answer for, I don't think we looked at this, but anyway, if you want to, we can look at it. These are people who contributed to different theories for the atomic model. J.J. Thomson. I'm not sure they might ask you these names, but anyway, let's just go to the ones that you may likely be asked. Positive charge of the nucleus could be subdivided into particles of positive charge. That's protons. And then finally, okay, this is someone, James Chadwick. Okay, all right. I think we answered this one, but let's just be sure that we got the right answers. Ionic bonding happens between them. They are so strong. It's because they have opposite charges. I think we said that. Directly positive, directly negative. Okay. If an atom loses an electron, it has a positive charge. And if an atom gains an electron, it has a negative charge. Okay, we said this. Covalent bonds happen between a non-metal and a non-metal, and electrons are shared. The most small covalent compounds like oxygen and water are gas and liquid at room temperature. We said this. Of course, that's respectively. Gas is for oxygen, liquid is for water. Okay. The reason for this is because the forces between of course, we said that they are weak, but the covalent bonds are strong. The larger the mass of covalent molecules, the higher the boiling or melting point. Okay, we alluded to that too. Okay, for giant ionic structures, okay, I don't think we answered this one, but yeah, it's lattices. That's the name of what they form. Lattices what they form. They have very high melting and boiling points because they have strong ionic bonds. Yes, they can conduct electricity when they are dissolved in water, or they are molten or melted. They are freer to move around. That's the reason why they can conduct electricity. Okay, we move on. Metals generally like to lose electrons. We've said that they like to lose electrons so that they can be stable. And by losing electrons, they form positive ions. These electrons are lost and are all donated into, okay, so I know I use the word pool, P-O-O-L, but the correct word is C. It's a sea of electrons, okay? It says, what are some properties of metal? We already know this. High melting point, stroke, high boiling point. They are malleable, they can be bent, and they are ductility. I'm trying to remember. What does ductility mean again? Okay. I can't remember this property, but malleable just simply means they can be bent into any shape. They are easily bent into any shape. Okay, let's look at covalent structures. Covalent structures act differently to simple, small covalent structure. So how do they act differently? Something like diamond is hard and has high melting and boiling points, as if it's a metal, but it's not, because of strong covalent bonds, okay? And but the forces between the molecules are strong too. Diamond cannot conduct electricity because it has no free, I think we said this, no free or delocalized electrons. Graphite and diamond are both made of carbon. We said that too. Graphite is soft. Remember how your pencil, the lead of your pencil is, okay, what we call lead, but it's not actually lead, it's graphite. It's soft because of the weak intermolecular forces between the layers, while it can conduct electricity because it has some free delocalized electrons. Okay, so just remember, once electrons can move, they can, what do you call it? They can carry or conduct electricity. Okay, so I think, oh, so I didn't, okay, I didn't even take note of this. Is this supposed to be relative molecular mass? Or I think it's the molecular mass. Okay, so it's molecular mass. So like I said, well, I can only guess the numbers, okay? But let me see. I'm not too sure you might be asked this, but let's just do for carbon dioxide, right? Okay, so I'm going to quickly go back to that slide that has the atomic mass for each one. So I'm going to go for carbon dioxide. Remember, carbon dioxide is what? CO2, right?
Yes.
Okay. Now, in your mind's eye, I want you to just see if you can do this calculation mentally, but if you can't, you can write it down. So the atomic mass for carbon is what? 12, isn't it? I mean, judging from what you have here, is 12. So if you look at carbon, there's 12. That's its atomic mass. Now, for oxygen, dioxide, that's O2. Oxygen, look at oxygen's own. Oxygen is, okay, oxygen would have been the next one. Sorry, it's not here. So oxygen is in group 8. Let's say group 8. No. Sorry, group 6, not group 8. Group 6. Its atomic number is 8. That's 2 plus 6, 8. But its group is 6. Okay, so that means that its atomic mass is 16. Okay, its atomic mass is 16. So what that means is that when you have 2 oxygens, O2, you are going to multiply 2 by 16, and that will give you 32. All right. Remember, it's the mass that we're after now, not the atomic number. Okay. So 16 times 2 is 32. When you add that 32 to the 12 for carbon, you will get 44. Did you get that?
Yes.
Okay. So that is the molecular mass, the molecular mass for the compound. Remember, a compound is when more than one element combine, okay? So the molecular mass for the compound CO2 is gotten by adding all the atomic masses for each of the individual atoms. Okay, so I'm only doing for carbon because at least we can, you can apply the same idea to the others, okay? And I bet you will get the correct answer. But just remember that depending on the small number that's there, for instance, for oxygen here again, you have another 2 there. So that means it's going to be 2 times 16, which is 32, plus the one for sulfur. Sulfur is, where is sulfur here? The sulfur, sure. Okay, so sulfur is also in group, where is sulfur now? Sulfur is in group 6 too, but I'm trying to remember it's, I think it's 286. It comes after phosphorus. So it's 286. So that means 286, that's 16. 16 plus 16 is 32. Okay. So if it's 32, let me see. Let's see if we can calculate is this thing. So for sulfur is 32, right? For oxygen is 16. 16 times 2 is also 32. So 32 for sulfur, remember we did not multiply anything because sulfur is just 1. To added to 32 from the 2 atoms for oxygen will give you 64. Okay, so again, that's how you obtain the one for all these guys, all of them. That's how you'll obtain the number for each of them. Of course, I know you're wondering, how did this one have a 0.5 since they don't usually have 0.5? Well, chlorine usually has a what you call a relative atomic mass because of the fact that it exists in a molecular, in its molecular form. It's and then this the isotopes, not the molecular form now. The isotopes of chlorine will give it away for not just adding it, taking its own atomic mass now. There's usually a calculation, maybe like finding an average that will make it to be added, and then by the time you divide by 2, you have 0.5. So for chlorine is 35.5. Then for hydrogen, it's 1. That's why you have 36.5 there. Okay, so I'll just move on now, so that we don't spend too much time on what may not likely or most likely be asked. Okay, if I'm just to say anything about this guy, for lithium, it's 2 moles of lithium will simply be 14, and you can see that from here. The atomic mass for lithium is 7, so 2 times 7 is 14. That's the reason why it's 14 there. Same thing that's happening back there. Okay. All right. This is the practical there that I said I could not remember, but well, you can. I'll give you I'll send this. I'll convert this to PDF and send it to you after the class, so you can just take a look at the.
Okay, thank you.
Yeah, welcome. Okay, so what is it for this guy? It says click to review missing words. Okay. Apparently, I need to. Okay, so when an ionic compound is melted, I think we looked at this, or dissolved in water. The ions are free, yes, to move about the liquid or solution. This liquid and solutions are able to conduct electricity and what are called electrolytes. Yes, passing an electric current through electrolytes causes the ions to move to the electrodes. Okay, so we said it. Cathode negatively charged and anode that the positively charged. I think we looked at these ones back then, so I'm not going to. And this is the answer for that one. I think we answered it, and we answered it correctly. I don't think we missed that. Okay. All right. I think we also answered this one. Yes.
Yes.
Answered this. Okay, there you go. That was what I was trying to draw back there. Okay, so the only thing I missed out in my diagram was what? The activation energy. But look at the exothermic reaction properly. You see that the energy that is released is given by that red line, and it is negative, okay? Because again, I told you that the formula for calculating energy of a reaction is heat of products minus heat of reactants. And heat of products, if you trace this back to the y-axis, you see that it is at a lower level than reactants, which is at a higher level. And a smaller number minus a bigger number will give you a negative answer. Then take a look at this one, which is like the opposite of exothermic. Heat of the reactants is lower than heat of the products. Why? It absorbs energy from the surroundings. That energy that is absorbed was not in the reactant. So because the products are the last guys to show up, the energy absorbed from the surroundings will end up inside the product. So heat of products will be more than the heat of reactants, which will leave us with a positive value for endothermic reactions. Now, I don't know if you can pick out something from what I just said. The fact is that even by me telling you the heat of a reaction, I can tell that that reaction was exothermic or endothermic. The reason why I'm taking pains to explain it like this is so that even if for any reason you forgot which one is which, you can quickly remember exo is outside, endo is inside. Exo means heat is released to the surroundings, is released to the outer surroundings. And that heat that is released shows that the heat must have been inside the reactant, which is usually the beginning of your reaction. So the heat of the reactants was more. So it now got released into the surroundings, then leaving lesser heat for the product for an exothermic reaction. So that way you will now remember, oh, heat of reactants will be more than heat of product. And that's what we usually give you a negative answer for HP, H products minus H reactants. And of course, the opposite is the case for endothermic reaction. Okay, so I actually got 2 materials for paper 1. So this is the, I'll send both of them. So let me close this since I'm done with it. I know it's going to ask me to save it, or let me just minimize it. Okay, so this is still paper 1, but I think slight emphasis on some aspects. Okay, so it says complete the dot and cross diagrams. Okay, so what is just simply saying here is that this is methane, the first alkane in the alkane family, homologous series. Okay, so what is between these guys is a covalent bond. It's covalent bonds that's there. All right. So to represent covalent bonds, we usually use X to represent the electrons that they're sharing. So what really happens here is that, I don't know if I can find a shape here. If I can use X, let me see if I can find a shape so that I'll quickly do it. Or let me see if this one has answers. Does it have? Okay, it doesn't have answers like that other one. Okay, so if I'm to draw a shape, right?
Yes.
I'm to draw X. Let's see. Insert. I'm looking for. Okay, let's see. Okay. All right. Okay, good. Okay, so what I was trying to say is this. Let me just draw this X. Okay, so you see that small X there? I'll just be using it anytime I need it. So the X, remember I told you X depicts a shared electron. So hydrogen always has 1 electron in its outermost shell. So that's X, the first X is coming from hydrogen. The second X, oops, sorry. That's what I didn't want to do. Let me take that out. Okay, nice. Okay. The second X is coming from carbons look like. One from carbon, one from oxygen, from hydrogen, sorry. Let's go to the next one. Okay. So in fact, I can even do this to save time. So, yeah. Okay. Can you see what I'm doing?
Yes.
It's just depicting where the covalent bonds will be. Now, I'm sure you're wondering, that should mean that carbon has what? 4 electrons. Remember that I told you that sometimes carbon likes to behave like like a metal. So it likes to give off. But in this case, it doesn't give off completely. It's a shared relationship. Okay, so that's what it's just doing. So carbon has 4. That's why it can take on 4 hydrogen atoms at the same time. And the hydrogen atoms can only take on 1 carbon atom at a time. So let me see. Okay, and then.
So to all of the hydrogens, every hydrogen is given out 1.
Yes, every hydrogen is giving out 1, and carbon has 4 to take care of each of them.
Okay.
Yes. Okay, so you got that right?
Yeah.
Now, if you notice, it says complete the dot and cross diagram. So dot is suggests that there will be some dot somewhere. So I want to just quickly use a dot. Let me see if I can use this as my dot. Okay. All right. So I'll use that as my dot. Maybe I'll make it slightly bigger. Or no, let's leave it like that. Okay. So for this guy, the dots are the electrons that are not participating in the bond. So for carbon we have 2. 1. What I want to do now. Okay, so I'm trying to see. Let me just copy and paste. What I copied. Okay, let me just do another one. Okay, so yeah, that looks more like a dot to me. All right. Okay, so let me do a copy. All right. So when I need another one, I'll just paste and move that to hydrogen, do another paste. Move that to hydrogen and do another paste. Move that to this guy and do another paste and move that to this guy. Okay. Oh, wait a minute. I just did something wrong. Hydrogen is in group 1. Sorry. It's not supposed to have. Yes. Sorry, my bad. That is wrong. So this is how it's supposed to look. Let me delete this. Let's delete that. Okay. So I'll just have these 2. Yes. Okay. So there you go. Did you see that?
Yes.
All right. Okay. So that's how it will look. Okay, so for Cl and Cl, oh, sorry, I skipped one. This is ammonia, right? The same thing that you did for, what do you call it? It's still covalent bond. It's the same thing we did for this guy. Is what we play out for this, okay? While for ClCl, yeah, this one has one electron, this one has one electron. Both of them will share. It's still a covalent bonding, okay? Still covalent bonds, no difference. Okay, so these are properties of covalent bonds, simple covalent molecules. They have low boiling point. Why? And that can be attributed to the weak intermolecular forces. So of course, the heat required to break those intermolecular forces is low. That's why you have low boiling point, obviously. Not much energy is required to separate the molecules. These three are these two are reasons for this. Okay, so think about it that way. A question might say, why is it that a gas like hydrogen chloride or water, usually they have low boiling points? This is the reason. You can explain it like this, and then further add this to buttress your explanation. Not much energy is required to separate the molecules. Okay. We're now moving to the next one, which this is just for emphasis. Describe how sodium reacts with chlorine. Okay, so how are ionic bonds formed? That's technically another way of asking it. I told you, ionic bonds are formed by, you can see that arrow there, suggesting that what? There's a transfer, okay? So you can now take a look at the sodium ion. You can see it has 8. If you count those number of circles, 1, 2, 3, 4, 5, 6, 7, 8. You see that there are 8. Now look at chlorine that has collected 1 electron from sodium, the sodium ion. If you count it, it also has 1, 2, 3, 4, 5, 6, 7, 8 in its outermost shell. And 2 of them are cool with that arrangement. Okay, so that's the reaction. Same thing here. Calcium oxide. I think this is calcium oxide. Okay, so CaO2. Calcium loses 2 electrons. Sorry, CaO, not CaO2. CaO. Calcium will lose 2 electrons. Remember, calcium is in group 2. So its outermost shell has 2 electrons. It now balances because when it loses 2 electrons from its outermost shell, the new outermost shell now will have 8 electrons and it's stable. Oxygen needs, oxygen, its atomic number is 2, 6. So that means it needs 2 electrons to balance out to become 8. So it will rather receive electrons than lose. Okay. So think about it. Another way to think about it is the difference between the number of electrons in the outermost shell will tell you whether it is more likely to collect or to give off. So the metals, apart from their obvious atomic structure, would like to give out. It's just 2 now. Let's give that one out. For them to get to 8, they will need more electrons, and that's usually a higher energy. Whereas for oxygen, it just needs 2 electrons to balance it, to make it 8 in its outermost shell. And that's why it will gain 2 electrons. Ca will now become Ca2 plus. The 2 electrons that it loses will give it a positive charge of 2 plus, while oxygen gaining 2 electrons will give it extra 2 electrons and give it a negative charge of 2 minus, or some people will say -2 or -2. Okay. All right, so let's look at what do you call it? Metallic. We said this before, but I think there are some things that were mentioned here. That's the reason why I went for this too. electrons from the outermost shell are outer shell are delocalized. Metal ions are positive and electrons are negative, held together by electrostatic attraction. Now, funny enough, this is what makes metals have a strong bond and a strong lattice, strong crystal lattice. So that's a giant structure that is formed will cause metals to have what? High melting point, okay, as a result. But they will be able to conduct electricity and heat energy, okay? That's quite important. Okay, so this is an experiment, test for water and test for carbon dioxide. Okay, so test for carbon dioxide, lime water goes cloudy. Lime water is Ca. It has something to do with calcium, though. So by the time you now introduce carbon dioxide, it forms a compound that makes the water, the lime water that was clear before, to become cloudy or milky in, from the looks. And so that's why you have that setup. But yeah, not too much details was given for the reaction, but so I'll just move on to the next one. Okay, we've also seen giant structures for covalent bonds, diamond and graphite, which we said. Okay, so this one focuses on diamond. It's a compound, not a compound. It's a form, okay? Let's call it a form of carbon, okay? A giant covalent structure. 4 covalent bonds per atom. You remember that we saw that from methane, CH4. It has 4 enough to share. And it's hard because of those bonds between the layers, and it has a high melting point. Whereas for graphite, 3 covalent bonds per atom. So that means 1 electron is free to move, okay? 3 covalent bonds per atom. But of course, the 4th one, which should have formed the 4 covalent bonds, will be free to move. And then it has, so that's why you cannot see it has free electrons, just like metals, okay, that can conduct electricity, okay? Okay, so surprisingly, the melting point is still high. I'm guessing that that's because of the electrovalent bonds, the covalent bonds, the 3 covalent bonds per atom, somehow still need to be broken. So, I mean, that will cause the high melting point. Okay, we've seen this. This looks familiar. Exothermic and endothermic reaction. Okay. All right. Let's look at this one. I think this is a okay. This is a question. It says the equation showing the structural formulae of the reactants and products is this: nitrogen having a strong bond, the covalent bond with 3 electrons, and oxygen having a covalent bond with 2 electrons, will give you NO, nitrate, nitrogen oxide, which is having a covalent bond with 2 electrons in it. Okay, so it says in terms of bond energies, explain why the reaction is endothermic. Well, remember, endothermic reactions are reactions that do what?
Pardon?
Endothermic reactions are reactions that do what? What do they do in terms of
They take in energy.
Yes, they take in energy, they absorb energy or heat energy from the surroundings. So looking at what you have here, look at the what you have here, the energy for the reaction, which I told you is what? Heat of the product minus heat of the what? The reactant. So look at it. 1443 is the heat of the product, while 1260 is the heat of the reactant, which is represented there, and it's positive. So I mean that equally gives you an idea why it's endothermic. Apart from that, you know, the fact that it absorbs heat from the surroundings. So the heat of the reactants was low. So for it to now absorb heat from the surroundings, the experiment will end with the product. So that means it's the products that will now have that heat that was absorbed from the surroundings, making the heat of products to be higher than that of the reactants. Okay, so this is just a definition for relative atomic mass, the average mass in grams of 1 mole of atoms of an element compared to carbon-12. So usually relative atomic mass is not far from atomic mass. That's the good thing about it. It's not far at all. Okay, I think we have done something like this. But in this case, they now gave us the values for each of them. So that's the difference between this one. So they did not stop it, but let me see. Let me see if I can. Okay. Okay, so we've done this. Let me do the one that I've not done. I think I've done the one for carbon dioxide. That's 12 plus oxygen is 2, and oxygen is atomic mass is 16. So that's 16 times 2. So I'll be quick to put that in a bracket, showing that that is for oxygen. And this would give me 16 times 2 is 32. 32 plus 12 is 44. For calcium, calcium is, now there's only one in calcium sulfate. There's only one atom of calcium. So that's 40. Sorry, let me separate it so that they don't look like that together. 40 plus sulfur is 32 from our table there. And then for oxygen, oxygen is 16 still, right? So that's going to be 6 times 4. And 16 times 4 is 64, isn't it?
Yes.
So that's 40 plus 32 plus 64. Okay. And that will give us what as the final answer? 0 plus 2. I'm just doing it, you know, without arranging it. 0 plus 2 plus 4. That's 6. 4 plus 3, 7 plus 6, 13. Okay, so that's 136 for this. Okay, for bromine, Br is 80. That's, sorry, 80, right? So since it's only bromine that's there, it's just 80 times 2, which will give us what? 160. Okay. Hydrogen chloride. Hydrogen is 1. Atomic mass 1. Plus, and there's only 1. Chlorine is 35.5. That's how we got 36.5 back there. Okay, then finally for sodium hydroxide, sodium is 23 plus for oxygen is 16, and then for hydrogen is 1. So that's going to give us 3 plus 6, 9 plus 1, 10. 10, that's 0 carry 1. 2 plus 1, 3, plus that 1 that was carried, 4. So that's 40. Okay. So usually this table will be given to you. I don't know why that last one didn't give the table. That's why I was a bit reluctant, especially when you don't have the whole periodic table in front of you so that you can be picking it from there. Okay. All right. So it says what? Work out the number of moles in 0.25 grams of methane. Standard form and 2 significant figures. Okay. So while I'm not sure this question might come up, right? But let me just let me see if I can solve it. Okay, so we know carbon's mass is 12. Hydrogen is 1. So that's 1 times 4, right? And that's going to give me 12 plus 4, that's 16. This is his relative, this is his molecular mass. What was called Rm back there. Okay, relative molecular mass. Now, number of moles, N, is, sorry, it's not supposed to be capital N, small letter, is equal to the mass, which is 0.25, divided by the relative molecular mass. That's 16. Okay. Okay, so do you have a calculator there?
Yes.
Okay.
It says 0.015.
0.015.
6.
Okay, 0.016, right?
Yeah.
Okay, all right. Okay, so that's going to be the number of moles. If it's two significant figures, yeah, we can leave it at that. Okay, so I think this is how they got the 35.5 for chlorine. You can see that when you have isotopes and we're considering them, then you have to look at it in this way. Remember, isotopes are the same elements, but different number of different number of neutrons. Yeah, different number of neutrons. So that's what gives it that possibility that the atomic mass for the same element can be different for the isotopes. Okay, so look at it. Remember, these percentages are percentage of occurrence, okay, in the natural form. So it will be given to you in the question. All you just need to do is to multiply the percentage by the atomic mass of each isotope. When you do that, you add them and then divide by 100. And that's how you get 35. 35.5. Okay. All right. Did you get that?
Yes.
Okay. So this is just the same diagram we saw for electrolysis. electrolysis, just showing you what's happening. Imagine a solution made up of positive ions, the red ones, and negative ions. Positive ions will go towards the negative electrode, while the negative ions will go towards the positive electrode, in this case, the anode. All right. And then, why are they going there? Attraction, electrical attraction. Oh, yeah. Okay. Remember, the way to remember it is unlike charges attract, like charges repel. Okay, so positive and positive, they will repel themselves, while positive and negative will attract themselves. Negative and negative repel. Okay, so of course, when they come to the electrodes, what happens? Depending on what they are, for instance, the positively charged ones, when they come, they collect electrons coming in to the solution from the negatively charged electrode, okay? And those electrons will make them to become atoms again. And that's why in electrolysis, again, I said it, electrolysis is a way of collecting the purest form of most substances. So if, for instance, you want to collect from a solution of sodium chloride, you want to collect your sodium back, you want to separate the sodium from the chlorine, and you want it in its purest form, just carry out electrolysis, and you will see that the sodium positive sodium ion will leave the solution and come and cling to the cathode or the negatively charged guy, electron, and collect electrons. And what will they become? They will turn back to sodium atoms. And when they keep on when that thing keeps on happening over time, the sodium atoms will now be coming together. And in most electrolysis experiments, you can even see it. You will see that the cathode will start becoming bigger in size. Why? Because sodium atoms are now clustering around it and forming the sodium metal on it. Okay, so it will be looking bigger than when you started the electrolysis. While what will be happening to the anode side? In the anode side, chlorine ions will be leaving the solution and getting attracted to the positive cathode, which is the anode. And what are they doing exactly? They already have extra electrons. They will be giving off those extra electrons that they have. And those are the ones that will now flow through the wire to the other one, to the negatively charged electrode. And when they give off those electrons, two chlorine atoms giving off each of their extra electrons will become chlorine atoms. When they come together with their covalent bond, they form chlorine gas. So after a while, all the things that you can use to detect chlorine gas will show that chlorine is giving off. You might even start seeing bubbles, in the solution forming, showing you that chlorine gas is forming, okay? And then I think I finally said that after a while, the solution will become, should I say, tasteless, because all the chlorine ions have left and all the sodium, this thing, have also left. So they have also left the solution, but somehow you would have found a way to collect them, either through a system, a way that you would have covered it. And then, of course, the sodium metal will be clustered around the cathode. Okay. So do you have any question?
No.
Okay. I'll send you this. They're both of them. Those were the only two I found. I'll look out for some for paper 2 foundation.
Okay.
Yeah,
Thank you.
that would be against the time when we'll be preparing for chemistry paper 2. Okay. All right. So I'll send them to you via WhatsApp so that so I know that we should be meeting tomorrow, right?
Yes.
Okay. So I'm thinking that maybe for tomorrow, maybe we should do a past question. I don't know if you have anyone that we've not gone through together, or can you get one before tomorrow?
Past paper.
Yes, for paper 1.
Okay, yeah. Should be able to, yeah.
Okay. All right. So we'll have something to we'll have some questions to solve. Still in line with the exam. Okay, so I think we can call it a day here. Stop sharing. Okay, so I'll be sending it to you via WhatsApp, the PDFs. I'll convert it to PDF. That's the format you would probably appreciate it. Okay, so enjoy the rest of your day. We'll meet tomorrow again by 6.
Yes, thank you.
All right, welcome.
Bye.
All right, bye.